Hello everyone, I'm Ramesh Raskar, professor at MIT Media Lab. And let's talk about participatory real-time epidemiology that can be achieved with privacy-preserving machine learning with techniques such as split learning and contact tracing. This work that's been done with many collaborators at MIT as well as PathCheck Foundation. So check us out at pandemic.mit.edu or join PathCheck at tiny.cc/pathcheck Slack. Now, when you think about data friction for COVID-19, think about chest x-rays. There are roughly 2 million hospitalizations. Nevertheless, the largest data sets are only about 14,000 images. And many models like COVIDNet were only trained on small data sets. So can we use trade secret preserving machine learning so we can actually create a much larger data set, train models that are going to be much more accurate, whether you're in China or Brazil or Korea or in the US, and we can all collaborate and create really great algorithms. So when you think about this privacy versus utility axis, for Google Maps, we willingly give away our location because we think it's a low stakes information. And in return, Google gives us fantastic utility, shows us all the traffic situation. On the other hand, when it comes to health data, privacy is very critical. We don't share it. It remains in a silo, and we don't get much utility out of it. So our goal is to create privacy-preserving machine learning that can achieve privacy and utility at the same time. And by privacy, we might mean information coming out of a device or a smartphone or an IoT device. But for hospitals and organizations, privacy can mean regulations. You cannot exchange information because of HIPAA regulations, for example, for health data. And for larger organizations who want to create data sets of biobank, you cannot just trade this data, exchange this data, because there may be trade secrets or even national security issues. So there are many reasons there's friction in sharing data, and the data remains invisible. So how can we make the invisible data visible? So if you think about the privacy axis, there are various ways to achieve privacy. We can anonymize, such as techniques like k-anonymity, obfuscate the data with differential privacy, and also encrypt with homomorphic encryption. But each of these methods have a different outcome in terms of utility, in terms of statistical queries, in terms of inference, and in terms of full-fledged machine learning. So two techniques have emerged over the last few years. One is called federated learning from Google, and the other one is called split learning from our group at MIT. And both of them have a similar idea, which is share wisdom, but not share raw data. So let's look at the situation with the current pandemic for exposure notification and case management. And the way you would achieve that is use smartphone to compute proximity, often using Bluetooth signals. Step 2, notify if you have crossed path with anybody who was later diagnosed positive, and achieve this while maintaining privacy and speed. Third is self-assess and diagnose. And fourth, provide all this information in an aggregate manner to public health or businesses for coordination. And this is what we mean by participatory epidemiology. It's a real-time epidemiology that maintains privacy and creates this so-called surveillance tool or health surveillance tool while maintaining complete privacy. For individual, the experience through COVID-19 is not just getting a test result or exposure notification, but there are many aspects of quarantine, exit, testing, in the future it's vaccines and so on. And the challenge is, how can we do all of this distributed computing in a privacy preserving way at every stage with no name or phone number or personally identifiable information? So if you think about trace and test systems, manual situations like I show here in the left column would involve contact tracing by identifying and locating contacts, then interviewing for context and testing and isolating. But if you do purely digital, there will be exposure notification, self-assessment, and self-monitoring. And our foundation, PathCheck, is achieving both of this with privacy and scalability. And in that sense, on one hand, we are developing apps on the left, and on the right, we are creating this real-time epidemiology tools using participation. And then we want to use various proximity technologies available to us. So Pathcheck Foundation, which is a nonprofit spin-off from MIT, is creating digital pandemic response with smartphones, and we're helping many states and nations launch apps. And it's an official app in 5 US states or territories, as well as 3 nations. And very quickly, it has become the world's largest open source nonprofit project for COVID-19. And we're very fortunate to have a fantastic team and long-term philanthropic funding. And also delighted to work with a really excellent team, former CEOs and CTOs and leaders in technology, software, and health tech companies. Now, there are many challenges and innovations that we need to develop, whether it's test verification workflow, with features for efficacy and behavior change, connection to manual contact tracing, customization for schools and campuses and employers, integration with tests and entry pass systems, and very rich insights for trends and required decisions about lockdowns or reopening and so on. So they require a lot of innovation that still needs to preserve privacy with AI preserving techniques. So at Pathcheck Foundation, we're working on solutions for individual users, for public health, for employers, as well as for tourism. So let's talk about some of the AI and machine learning techniques that we're developing through MIT SafePaths. And as I show here, first of all, dealing with proximity with GPS and Wi-Fi and QR codes, and then creating privacy-preserving machine learning techniques is very critical. If you don't have location context and contact tracing, actually it can create a lot of hazards. So we have new techniques that uses encryption, encrypted additions to Bluetooth broadcast. And here the GPS information is used for location context, but not for proximity. You can also use Wi-Fi information for local collocation without prior scanning. And the 2 methods that emerge, one is phone-based and one is access point-based. And in the phone-based systems, the phones can record the access point MAC address. Nevertheless, MAC addresses are prone to search attacks. So the solution is to use an external server that provides a randomized token based on IP address. And if the solution is based on access point, then it's very difficult to maintain privacy, the privacy of the smartphone of an infected person will still be leaked, unfortunately. So we have proposed a solution based on secure multi-party computation, and that uses GPS or Wi-Fi using a 2-server solution, and it provides best privacy for healthy phones, but still some leakage for the infected person. So what about using full-fledged machine learning, training deep neural networks without exchanging raw patient data on the phones, not just proximity, but such as questionnaires and information you might recover from sensors and video and audio for diagnostics. So as we saw earlier, 2 techniques have emerged to deal with it, split learning and federated learning. Let me explain how split learning and federated learning works. In centralized computing, if you want to create a master algorithm for exposure notification or for chest X-ray detection, pneumonia from chest X-rays, you would centralize all of that data on a single server and just train a machine learning model. The idea behind federated learning is that the data, in this case chest X-rays, may be distributed across 100 different hospitals. The first hospital may have diabetics, the second has smokers, the third have elderly patients, and so on. So although each of them have very unique data sets, we want to create a global AI model. And the idea behind federated learning is each of these hospitals can train a partially trained model and then share those weights of the network with the server. And server can mostly average those weights or activations, but do not look at raw data. So this provides a great solution where without looking at raw data, the hospitals are able to provide the wisdom, and this collective intelligence gets averaged at the server. Split learning from our group at MIT is slightly different. And we have a notion of a split wisdom, where every one of these X-rays from every one of these 100 hospitals will convert the X-ray into a feature vector. And that feature vector is transformed into something called smash wisdom. And the idea behind smash wisdom is we're going to smash the bits from these feature vectors into unrecognizable information. And this smash wisdom is sufficient to train a master AI algorithm. So again, we would take the individual X-rays, smash them into smash wisdom, and they would be transferred to the server for training or for inference. And in this case, we would take a deep neural network and split that. An early part of the network will execute at the hospital, and the later layers of the network will execute on the server. And that's what we call a split learning. There's a split in the neural network itself. And when we think about decentralized machine learning, there are many challenges when it comes to compute and bandwidth and memory and accuracy and so on. And just the same way decentralized ledgers had transformed blockchain, decentralized machine learning can really transform how we think about health data and other distributed machine learning techniques. So I won't go into the detail, but for compute and bandwidth and data and machine learning, there are many challenges, especially the one I highlight here in red. And that's where the distinction between techniques like split learning and federated learning starts becoming visible. So in many scenarios, when you have heterogeneous data, such as one hospital has just diabetics and the next one mostly has smokers and so on, it's very heterogeneous data. And also you have scenarios where there are very few hospitals, of the order of hundreds of hospitals as opposed to millions that are collaborating with each other. And what we have shown in these scenarios, split learning actually does a much better job compared to federated learning techniques. And then we have shown this on multiple medical imaging benchmarks as well. So going back to the problem of COVID-19 chest X-rays now, imagine if we use a technique like federated learning or split learning. In split learning, you would convert every chest X-ray into a feature vector and a smash wisdom, and that smash wisdom can be shared with anybody in the world. And hopefully, when thousands and thousands of such chest X-rays are shared in a smash wisdom form, researchers and epidemiologists and doctors can create very sophisticated algorithms to see if a chest X-ray corresponds to a pneumonia corresponding to COVID-19. And in a fast-moving, a fast threat like an epidemic requires this coordination in a computational manner. At the same time, when it comes to other techniques for COVID-19, such as exposure notification, contact tracing, testing, vaccines, or any aspect of digital pandemic response, we also have to think about privacy and decentralized AI. So to conclude, we have an opportunity to take information on smartphones or hospital and create a participatory real-time epidemiology. It's not a top-down solution, but a bottom-up solution created on smartphones or hospitals. And what we discussed was privacy-preserving machine learning techniques that do not force an individual or an organization to give up their raw data, but still contribute to the global wisdom through smash learning. So split learning that creates smash wisdom, or contact tracing that allows exposure notification using protocols that preserve privacy. We have a long way to go to bring many of these ideas to the health domain. But nevertheless, privacy and AI will play a very critical role in digital health. I invite you to look at our website, pandemic.mit.edu. And because PathCheck Foundation is one of the largest open source nonprofit, there are thousands and thousands of contributors that are working real time. So if you're interested in joining us, go to PathCheck Foundation, or you can join our Slack channel, tiny.cc/PathCheck Slack, or you can download our apps or check out our source code on GitHub. Thank you.